would like to thank the organizers for this very good workshop. It's been great to talk to many people so far. I would like to give a very informal talk, so if you have any questions, please just interrupt me. So I will talk about six-vertex model and convergence to the GFF. And it's joint work with Hugo Duminil-Copin, Karol Kozlowski, and Ioan Manolescu. Yes, so I appreciate that people here have different backgrounds. So I first would like to introduce a bit sort of the wider area. Does this work or not? Yes, okay. So I will first talk a bit about six-vertex model and its relation to FK percolation. Then I will give definitions and main results. Then I will give a short primer on conformal invariance. And then, yeah, I would like to explain some things of the proof. So first, I will explain a bit the relation with FK percolation, and I took some images from the paper of Gurab and Yino. So I think most people are familiar with 2D FK percolation on the square lattice. And I will, yeah, here we see immediately the primal percolation in blue, and then there's the dual percolation in red, and there are the interfaces which separate them. And in fact, if you do it like this, you can put yourself immediately at the critical point by just putting the weight of square root q to the number of interfaces. So in fact, if you count the number of interfaces, this is twice the number, no, yes, I think it's the number of blue plus the number of red clusters. And if you work out the critical percolation weight, then this percolation weight disappears, etc. Of course, the important examples are Q equals 1, which is critical percolation. There's the critical icing model, and then you have the critical four-state Potts model and Q equals 4. And it has long been conjectured in the physics literature that you have the critical exponents. And it was later conjectured that this model satisfies some conformal invariance properties. And later, with the onset of serie kappa, there was also an explicit candidate for this convergence. So none of this has been proved, to the best of my knowledge, except in the case of Q equals 2, where we have the icing model, and there's somehow more structure that can be analyzed. Okay. So in fact, one way to see this model is by saying, okay, we have a weight on loops, but in fact we can further decompose this weight into loops of two types, where the loops are either left or right turning. So to do that, we want an equation of the form, square root of q is equal to the sum of two things, right? So for example, for q equals 4, square root of q equals 2. And then this formula becomes very simple because I can do weight of 1 of left and then weight of 1 on right. But in general, you can assign some complex weight. And this gives you a complex measure whose marginal is just the loop measure without the orientations. And just like in Martin's talk yesterday, if you have oriented loops, you can say, in fact, it encodes the gradient of a height function. Because just the way you do it, you can imagine that you look at an atlas and you have the height lines, and then whenever you walk over directed loops, you can just imagine that on the right it's one higher than on the left, right? So if you're following a loop, you're kind of on a mountain, but you're always keeping the higher one on the right. And now what you can do is also something different. You can just keep the structure of the height function, but you forget about the way that those loops were connected. So, like for example here, you have the incoming and outgoing edges, but you forget how they were connected. And this gives you another model, which is called the six-vertex model. This coupling, called the Baxter-Kellens-Book coupling, it gives you an identity on the level of partition functions. But if you go a little bit deeper, you see that there's also some identities between certain observables. Right? So this identity is quite rigid, but still there are some things that you can push forward. For that you can look, for example, in the work of Duminil. Okay, so this is mainly to motivate a bit the research that we do, but later we will see that the two models are really quite important.
You said the directed loops are distributed under a complex measure?
The directed loops are distributed in a complex measure.
And once you pass to the height function, it becomes real again?
That's right, yeah. So you have a complex measure, but the two marginals are probability measures. Okay. Yes, so let's now go to a definition of six-vertex. So it's a step-back model on Z2. The configurations are orientations of the edges, so every edge points one of two directions. We have this ICE rule, which is basically the rule that makes that you can consistently define a height function, or that it makes sense in terms of loops if you want. And like I said before, we have the rule that on the right of an arrow you're always one higher. And we put a probability measure on that. I don't want to say how it's parameterized with the Q and the FK, but you're basically counting the number of saddle points. So for example, this point it's not a saddle point, but this point it's a saddle point because you go one up, one down, one up, one down. Okay. So it's quite natural to say that, okay, if there are more saddle points, then the function is kind of flatter, right? So if C is big, then we're favoring a very flat height function, and the behavior should be different than when C is very small. Right, and if you're interested in this from a field theory perspective, the first thing you do is to define the correlation functions. So in this case, it's just definition. But what you do is you say, okay, I'm going to fix k pairs of points, and for each pair, I'm going to look at this, the expectation of the product. Right. So for example, if I put one pair here and one pair there, right? So k is equal to 2, and then I put u1 prime, u2 prime. In fact, I'm just calculating the correlation between this edge and this edge. Right? So I calculate the probability that the arrows point in the same direction, or maybe that they point in the opposite direction. Yeah, but this formula is okay. It's a definition, but it's a bit more general. Okay. So this model you can easily simulate on a computer. And here I took 3 samples of this height function with fixed boundary conditions using many iterations. There's no guarantee that this is sufficient. I just hope it's good enough. This is a zoomed-in version of one of them. And in fact, there's quite a general expectation that such height functions are either very flat or they converge to the Gaussian free field. So okay. I guess that many of you will be familiar with this. Yeah, so the natural questions to ask are the following. What is the natural scaling limit of H? Is it conformally invariant? What is the dependence on this C parameter, which promotes the saddle points? And what is the dependence on boundary conditions? So in this talk, we will be able to answer the first 3 questions, more or less. However, boundary conditions are still extremely difficult to handle. Okay, so I will now give a quick definition of the GFF. So it's a Gaussian process, right? So it means that in the limit we're going to see something Gaussian. But there are some problems with this definition. It's not defined pointwise, and you can only define its gradient in the full plane. I just want to advertise 2 possible solutions to this. First, you can look at circle averages, but what you can also do is that you look at the correlation functions. So in fact, the problem with this, with the log is that when you put 2 points in the same place, then you get infinite variance. Yeah, so one thing you can do is you can locally smooth out your field, but you can also say, well, if I look at correlation functions and I don't put my points in the same place, I don't care about this variance. Right? I can express this in my covariance matrix, but I'm not looking at the diagonal. And these correlation functions, they're still somehow of order 1. So they're just different ways of looking at the GFF. Okay, so there's a conjecture. So when C is between 0 and 2, there should exist a constant sigma, such that the height function converges to sigma times a GFF. So you have the Gaussian free field as a scaling limit, but there's this scaling prefactor. And what this means for me is that the correlation functions converge, and also there's convergence in the sense of test functions. So, okay. I will mainly focus on the correlation functions in this talk, but I think for many people the test functions will also be familiar. So what I want to advertise is that this is known around at and around the free fermion point. So at the free fermion point, it's the dimer model, and it was later generalized to a small neighborhood of that point later on. Okay, so the result that we prove is that, in fact, for C, so it was conjectured between 0 and 2, but in the range square root of 3 and 2, we prove convergence to the GFF, and we also have an explicit constant for sigma. This will also be important later on, but I don't want to discuss that more. But in particular, we get convergence of the correlation functions and also convergence of the test functions. And also, we get convergence in the appropriate Sobolev spaces. So,
C bigger than 2, what can you say what happens?
yes. So for C bigger than 2, the height function is very flat. And in the FK model, this corresponds to a discontinuous phase transition. So, in fact, height functions, they're naturally always critical. But for C smaller than 2, it's a continuous critical phase transition, which means delocalization. And for C strictly bigger than 2, it's a discontinuous critical model, and that is localization.
So for C bigger than 2, you expect exponential decay of correlations. Is that which?
Yes, but all of that has been proved. There's, for example, a paper of Alexander Glassman and Ron Pellet, where they explain how it's related to the exponential decay in the FK model for Q bigger than 4.
Now here you only have one parameter C.
Yeah.
Remember in general 6 vertex you have 3 or 6, 3 or 5 parameter, more than one parameter.
That's right. So in fact, we also proved that for a larger range when A is not equal to B. So in fact, one way to see it is that we proved the result on the square lattice, but you can also make sense of the model on a square lattice, but you kind of rescale one of the coordinates, and then it has a natural expression in terms of A and B. Then we also proved the GFF convergence. But this is quite directly related to the symmetric case because of Young-Buxton equations. Thank you. Okay, so yeah, this picture, it's basically when you zoom out, it should look like a GFF. Okay, so first I want to stress one point. In physics and mathematics, there has long been this idea that if you have rotation invariance in your model and scale invariance, then this gives you conformal invariance. And basically it's because if you zoom in a complex analytic function, then it looks like locally like a rotation and a scale. And in fact, physicists often thought that scale invariance would be more would be easier to get. Basically that this would be automatic with tightness of the model, because of course if your thing is tight then it also converges. And in fact, now from a mathematical perspective it's not so clear which one is easier to get, but we somehow started the project knowing that the model had rotation invariance and scale invariance in some form. Okay, so I'll explain that in a second.
Wait, so why is it, why do you have like characterization of the subsequences? You said if it's tight it converges, but...
Yeah, that was somehow a physical expectation.
Okay, yeah. So you just have a characterization. Thank you.
There was this expectation that tightness would imply convergence.
Okay, okay. I see.
Yeah, so I will explain where the rotation invariance and the scale invariance come from. So in fact, rotation invariance was proved for this FK percolation for Q between 1 and 4 in a recent paper of Hugo, Ioan Manolescu, Karol Kozlowski, and I think Alex Carilla. I apologize because I'm not certain. So what they did was they used basically an analytical tool called the FK inequality and the Young-Baxter equations to prove that the loops, they're somehow invariant under rotating the model. And this automatically gives that any subsequential scaling limit of the correlation functions is also invariant under rotations. Okay. So this is really the rotation invariance of the model in quite an explicit form. And in fact, a posteriori, we realized that the scale invariance was also there, but somehow in a much more subtle form, because there's this free energy functional. So it tells you basically the free energy of the model when you impose a slope. Right? So you can say, okay, here we impose 0 boundary conditions, but you can also imagine that you impose kind of a slope. And this free energy is twice differentiable. So how it responds to the slope you can differentiate twice. And if you differentiate twice, it means that some limit converges as you take the slope to 0. And this is somehow some form of scale invariance. Okay. So in fact, yeah, as we shall later see, this is somehow sufficient. So yeah, a posteriori, it's not clear if physicists were right or wrong in saying that the scale invariance was easier than the rotation invariance, because I think both are quite subtle results, but at least this is how they come in. Okay. So in some sense, this article is about proving, this project is about proving how you can combine those two ingredients into getting conformal invariance and then also the convergence, because it's even possible that all subsequential scaling limits would be GFF, right? You have conformal invariance of any subsequential limit, but you don't have GFF, right? For example, it's possible that any subsequential scaling limit is sigma GFF, but with a different sigma. I mean, then you still don't have the scaling limit. Yeah, and also, so we use this FK result, but also, yeah, we already, I mean, it's part of a bigger project, and we already know that you can prove and calculate the one-arm exponents in critical FK percolation for Q between 1 and 4. And the hope is kind of that also other critical exponents can be calculated, and maybe, it's a more ambitious project, that it's possible to characterize really the scaling limit of the loops. Right, so this has been proved, for example, for the icing model on Z2, and also for percolation, side percolation on triangular, that is what Hugo talked about yesterday. Yeah, let me mention that for the critical exponents, because there are scaling relations, it typically is sufficient to characterize 2 critical exponents. However, the one-arm exponent is not one of them, so there's still somehow 2 exponents to do before this is done. Okay, so I want to sort of give an overview of the proof. So first of all, we will focus on the correlation function. So once we have convergence of the correlation functions, it's relatively straightforward to see also that the convergence in terms of test functions and Sobolev spaces will also work. And the first thing is that these correlation functions can be expressed in terms of transfer matrices. So transfer matrix, it's simply, I will explain in a second, but it's a linear algebra tool to analyze your system. So you can use your standard theory of Hilbert spaces. And at the same time, your model can also be expressed in terms of a spin representation. So this is something that Martin also talked about yesterday. You can somehow use tools of percolation theory, such as FKG inequality and RSW theory, to understand your system. So I think the message is that we have two ways to express our correlation functions, but those two ways are really extremely different. A priori, they don't communicate with each other at all.
When you talk about spin representation, what do you mean by spin? Do you mean the arrow configurations or the random cluster? What is spin?
Okay.
It's not the height, I guess.
So I did not introduce this at all, and I don't want to focus too much on the talk. But basically what you do is the following. You find some kind of, you want to characterize in some sense the level lines of the system. So before we said the loops are the level lines, right? You had these loops in your loop model. But from the perspective of FKG inequality, this representation is not so good. So you want to find a different way to represent your model. And the way to do it is to look at your height function modulo 4. So for example, if you look at an even phase, there's always going to be an even value. So modulo 4, it's going to be 0 or 2. So you can represent this somehow by plus and minus. And now if you look at all the spins at the even phases, so you forget about what happens at the odd phases, then this satisfies an FKG inequality. So broadly speaking, it's somehow a way that then you relate this, so you have some kind of Ising models. You can look at some kind of FK representation of that, and that allows you to go back to a percolation. And then you can use your standard techniques. Okay. So we have these two tools to represent the correlation functions, and they're quite different because in the case of transfer matrix, you can analyze the spectrum. It gives you exact identities, and you can use, okay, I called it algebraic tools, but it's just Cauchy-Schwarz and finite dimensional Hilbert spaces, so this is quite basic. And in the end, it gives some, okay, I called it algebraic structure to your correlation function. So for example, you can prove that limits of correlation functions are, for example, differentiable or maybe twice differentiable. On the spin representation side, we're going to analyze percolations. You don't really get identities, but rather you get bounds. You have Russo-Seymour-Welsh theory, and in the end it gives you some regularity structure. So for example, you can prove that your subsequential limits of the correlation functions are, for example, Hölder continuous. What I want to stress is that, in fact, if you look at the logical ordering, basically we first do this spin representation analysis, right? So a priori you only know that you have Hölder continuity, but then later you want to prove that you can actually upgrade here to really sort of the differentiable structure. So are there any questions at this point? Okay, so the global steps. In fact, the most difficult part in the proof is to prove that the two-point correlation function converges to the one of the GFF subsequently. So that is really just the covariance matrix somehow of the GFF. And in fact, a priori we don't prove convergence to the one of the GFF, but rather we prove a dichotomy either you have the convergence to the GFF. So if you take your correlation function and you zoom out, you get precisely the one of the GFF. Or you consider the set of all subsequential limits, and we prove that this set contains two scalings of the GFF. Right? So I'm not saying that all those subsequential limits are multiples of the 2-point GFF correlation function, but just I can find two subsequential limits which are multiples of the GFF. Okay, then in the second step, we prove that in fact, if you are a multiple of the GFF correlation function for the 2 points, then it happens for all the higher point correlation functions as well. So if you combine those two results, you know that either all your correlation functions converge to GFF, or well, you have a sigma minus and a sigma plus, and then all the correlation functions converge subsequently to those of the GFF. And then finally, what we prove is that if you have GFF convergence along some subsequence, then you have an identity for the sigma in terms of the second derivative of the free energy. Right, so of course, well, if you would be in this second case here, then this last thing, it would tell you that sigma plus equals sigma minus. Right, so the second case, it's not really possible, and you must have really convergence of the.
This is the derivative in what, in the tilt, or?
Yes, it's the second derivative in the tilt. Yeah.
The tilt is a priori vector, but I guess it's because it's rotation there, it reduces to a single.
So, in fact, what is quite a subtle point is that the free energy, it's kind of a large deviations principle, right? It's about characterizing events of order e to the minus the size of your system squared. And this GFF convergence result, it's about events that are of order 1. So, in fact, yeah, of course, the directional derivative should be the second directional derivative should be the same in every direction. But this is also only true at the critical point, right? Because as far as you go away, it's not critical anymore. But yeah, basically
But that uses the rotational invariance or something like that, because on a discrete system, I guess, it's not the same in all directions, I guess, right?
Yes, yeah. But yeah, that's right. Here we just use a directional derivative. So it's just you tilt along one coordinate axis. And yeah, so there's this step 3. It's kind of a way to connect the LDP to the probabilities of order 1. So what I want to stress is that we get an explicit value for sigma, but somehow the tools that I presented, the transfer matrix and the FKG, these are kind of soft tools. So they would never give you an identity for sigma, right? They would just maybe tell you, okay, there's some sigma, but not what it is. So in fact, there's one place where we use Bethe Ansatz, and this is this last step. So Bethe Ansatz, it's a very computational tool that can give you exact numbers. But we only use it as the last step. So somehow we were able to do the rest of the program without using Bethe Ansatz. Okay. And yeah, what I want to stress is that although it's a little bit hidden here, we also use the FKG inequality everywhere. Okay, so these steps, they use the transfer matrix, but also the FKG inequality. Yeah, so in the remainder of the talk, I want to focus a bit on this first step, to study the 2-point correlation function. So are there any questions up to this point?
I guess, so I'm not that familiar with Bethe Ansatz, but why do you want to avoid using it?
I mean, when you're a scientist, you always come with your own backpack of tools. And I think that Bethe Ansatz uses transfer matrix, but it's really an extremely computational tool. But the transfer matrix itself, okay, it's really just basic linear algebra. You have matrices, you have a symmetric real matrix, so the eigenvalues are real. I mean, this kind of stuff, it's really much more basic. So we try to kind of see, okay, what is the essential information of this complicated tool? It's the second derivative, but for the rest, we don't really need it. Like, we're really just analyzing the eigenvalues of a simple matrix. Like, okay, that's somehow sufficient.
So speaking of FKG, so Q between 0 and 1 would map to which values in this mapping?
Yeah, so why is C bigger than square root 3?
Is that Q bigger than 1?
That's Q bigger than 1.
Okay.
Because for Q smaller than 1, you lose the FKG inequality, and you lose the rotation invariance result. So in fact, the spin representation also has FKG, but it has FKG up to C equals 1. Now C equals 1 corresponds to, I think, negative or complex value for Q. So in fact, if we could generalize...
So including Q between 0 and 1, but up to the...
That's right, yeah. So the free fermion point, it's Q equals 0, I think, right? And C equals 1 over square root 2. But you can even go below that. And in fact, if you get rotation invariance for C between 1 and square root 3, you will also automatically get GFF convergence. So that's the only part somehow missing from...
So you don't need the FKG for the random cluster model, you only need the FKG for this spin representation.
That's right. That's right. And then C smaller than 1 should somehow be more difficult. Okay. Right.
So can you use free energy derivative to prove rotation invariance? Or what's missing there? So you only use the second derivative of free energy to get some rotation invariance. Missing.
So I think Bethe Ansatz probably allows you to calculate the second derivative in the coordinate direction.
I see.
But I'm not sure if you can do it in a different direction.
Okay.
And even if it wouldn't give you rotation invariance of the correlation functions directly, I think. So in fact, in this third step, we use quite a lot the fact that we already have the GFF convergence. So this gives you a lot, I mean, there's one variable left, right, which is the sigma. So there's a lot of rigidity already. Okay, so let's focus on the two-point correlation function. So first, what is a transfer matrix? Well, put your model not on Z2, but rather you put it on a cylinder. Right? So you put it on Z times Z over LZ. Now, this model is essentially a one-dimensional model, right? Because you can put something here on one column, and then you have the next column, but then you get the Markov property, and your model is essentially, okay, I like to see it as a one-dimensional Markov chain, right? So basically here, in this column you have a bunch of arrows, and then in the next column you also get a bunch of arrows. And then you want to characterize somehow what is the weight of this transition, and this is characterized by what is called the transfer matrix. And in fact, what I want to stress is that there are two fundamental operators. They're really quite simple. There's one which allows you to go to the next step. And so this one is defined in terms of the weights of the six-vertex model. And there's one that allows you to shift everything up. Right? So you have the cylinder, and then you just shift everything by one. And they commute. Why do they commute? Well, it's just actually shift invariance of the six-vertex model.
So shift by one, you mean it's a spatial translation in one direction?
That's right. And what you can do is that phi k, so the correlation functions, they can be expressed in terms of such operators. Okay. So, before doing this project, I was not so familiar with working with transfer matrix, but in the end, it's really just basic linear algebra. So what I want to stress is, for example, look at this upshift operator, right? It shifts every configuration up by 1. What are the properties of this? Well, if I do it L times, I just shifted the thing to itself, right? Because, well, it's a cylinder with circumference L. So T0 to the power L is just the identity. So if you look at the eigenvalues, they're going to be Lth roots of unity. Now, what's a property?
Just say again, because I didn't catch what are the two operations, in which direction? So you have your L periodic, so
yeah,
C, and then it goes in the infinite direction in the other. Okay, and now the
yes.
What are the two shifts in this direction? I didn't get it.
So
in the infinite direction, are you doing a shift? Which one of these?
yes.
Is it 0?
Sorry, T0.
What are these two shifts?
T0, what it does, it basically, you have a matrix, you have a Hilbert space.
Which is given by the configuration of one of these circles.
Yeah, so
one of these N plus 1, yeah.
Exactly, the basis of your Hilbert space is the arrow configurations on that column. And now this matrix, it's a matrix where there are zeros everywhere, except that the entries where, like, if you look at the row and the column, they differ by 1 shift. Right, so it's kind of a permutation matrix of in this basis.
So one is a time translation, one is a space translation.
I don't see it as...
2 is the time translation of the Markov process, and the T0 is the spatial translation.
Yes, yes.
So spatial translation, you're kind of rotating these endpoints.
Yeah, you just...
And the other, you're just shifting it around this time direction.
Yeah. Okay. So now I'm just going to present a formula and say that the formula is true. So, okay, obviously what you want to do is that you have these matrices and also this T pi over 2 matrix, so it adds one thing. It's a real symmetric matrix. So why is it a real symmetric matrix? Well, you can just write your thing out in this basis, and then you just check it's a real symmetric matrix. So it means basically that yeah, it's immediate in terms of the weights of the 6-vertex model. Right, your 6-vertex model, it's like it has lots of invariants, like a shift invariant, flip invariant, etc. And this just tells you it's a real Hermitian matrix. Okay, so now we have a Hermitian matrix and a matrix with eigenvalues in the unit circle, and they also commute. So you want to go to a common eigenbasis. And when you calculate correlation functions, you're actually going to sum over the eigenspaces of this matrix. Because in the limit, you're calculating the trace of a matrix, and then you just sum over all the eigenspaces. So I was a bit lazy and I wrote the sum as a measure. So in fact, this sum, it's just this measure is just a sum over Dirac masses. Right? It just tells you, okay, there I have an eigenvalue, so I put a Dirac mass there. And if I have 4 points, right? So we're calculating a 4-point correlation function. Then I can write it like this. Right? So if I go from here to here, for example, if I go from there to there, right? I just need to apply my matrix. But now everything commutes, so I can just write it like this. And yeah, actually in this mu-L measure, okay, without telling you, I sort of put some other operator which allows me to measure the height. Right, so if I calculate this thing, I have the product of 2 differences. I can expand the product, it gives me 4 terms. And I could do the same here. It would also give me 4 terms. So yeah, for example, there's one term corresponding to this, one to that, one to that, and one to that. Okay. So are there any questions about this formula, which I'm not going to prove? Okay. So we can ask a simple question: which eigenvalues are going to dominate this formula? Well, if the distance between the points is of some order, then in fact, well, if my eigenvalue is very small, then clearly this factor in the middle is going to be very small. However, if my eigenvalues are super close to 1, then this thing will be close to 1, and therefore this factor is going to be small. So in fact, in this formula, we can see that there are certain eigenvalues which are going to dominate this, this measure. And those are the eigenvalues which are not too close to 1 and not too far away. And in fact, we can just see that they have to be of order 1 over the distance between the points. Okay. Wait, 1 sec. Yes. So before going further, let's imagine for a second that A is equal to the absolute value of B. So let's suppose this is true. Well, then in fact, what do we have here? This is just an awkward way of writing A times a complex number, right? Because here we have, okay, we have x1 in the horizontal direction and then y1, but in fact, of course, this is just equal to x1 plus I times y1. So if A is equal to the absolute value of B, then I want to write my my points in the complex plane. By the way, here there's a typo because it should be x2, not x1. Right? So there and there should be a like the apostrophe. So in fact, you can kind of write your formula with complex numbers, right? The position of the points, they are now complex numbers. And okay, because you took this absolute value of B, and then, okay, maybe you kind of like kill this complex conjugation symmetry, you need to take the real part. But suppose that this formula is true. Then it tells you that your correlation function is the real part of a complex function. And in particular, it's a harmonic function. And this is great news because there are not so many harmonic functions in 2D. So if you can prove that this 2-point correlation function is harmonic, this is already an extremely strong information on what those correlation functions should look like. So in fact, what a lot of the project is about is to sort of justify this in the scaling limit. So to show that in the scaling limit, the eigenvalues, they behave like this. And when you have this, then basically you have the harmonicity structure. And this is the key part. Yeah. So yeah, like to, yeah. So in fact, there's a little detail because in fact here things are defined on the cylinder. So before doing all this, you want to take L to infinity. Now you could a priori try to make sense of the L to infinity limit of the operator, but we don't know how to do that. But in fact, we don't care about the limit of this operator because we only want to see somehow some like some observable in terms of this operator. Because what we really care about is the limit as L goes to infinity, so you're unwrapping kind of the cylinder of the 2-point function. So in fact, what you want to show are two things. You want to show that this mu L converges in some space. And once you have proved that the mu L converges, you want to show that your integrand was in fact good enough that the integrand also converges as mu L converges. Right, so there are kind of two questions to ask. Does mu L belong to a compact set of measures? Right, so can we take a subsequential limit of the mu L? And secondly, we want to integrate some stuff. Do those integrals also converge? So let's first ask the first question. Does mu L belong to a compact set of measures? Well, in fact, let's choose a particular correlation function. So, in fact, let's choose a very simple two-point correlation function. Where the 4 points, so it's U1, U1 prime, U2, U2 prime. And they're on the line, and the distance between them is 2k. Now, before your integrand looked very complicated and it involved complex numbers, but now we just get this formula, right? And in particular, the integrand is always a positive number. So it means that if we know how to control this thing, if we know how to control the two-point function, since this integrand has constant sign, it also allows us to bound maybe a in some interval. Right? So what I said before is that if the distance is 2k between them, then the main eigenvalues are going to be between 1 over k and 1 over 2k. And it allows me to get a formula like this. And in fact, we also know how to bound this correlation function using FKG inequality. Right. So physicists, they were often interested in exact calculations, but when you do that, you want to take limits and you run into problems such as dominated convergence theorem, right? Or like things not blowing up. And the solution to that is that you do a probabilistic analysis. So you do a FKG, inequality, RSW. This gives you bounds on the correlation function. And this proves you that the spectra of these measures belong to certain compact sets of measures. Okay, so now we also need to ask the second question. Which integrals converge? Okay, this was, for the first question, I just give an example of how we do it. I mean, of course, there's some more things you need to do. But, like, generally the idea is that you use bounds of this form to bound sort of how much mass this measure has in a certain interval, and then you prove that this is compact. Right, so then you also need to ask, okay, the measure converges, but does it also mean my integrand converges? So in fact, this is quite delicate because we get that for the two-point function, the integrand only converges if one of the yi's is 0. So it means that basically you're looking at correlation functions like this, but one of the pairs, they have to lie on the same line. Okay. And yeah, then you kind of want to work your way back up to get also the ones where they're not on the same line. Okay, so I think I don't have much more time. So what I will mention is that once you have done this, you also want to take the scaling limit, right? So you can make sense of this even when when you blow up your points, right? So they are very far away from each other. And then the key thing is to prove that A equals B almost surely. Right? So you have this limit of the measures, and you want to prove that this happens almost surely in the measure, so that you can recover the complex / harmonic structure of the two-point correlation function. This, it relies on rotation invariance. So the rotation invariance somehow allows you to do a deep complex analysis argument, where in the end you use pole integration to prove that almost surely the modulus is the same.
Probably is almost equivalent, right?
Sorry?
It's probably almost equivalent to rotation invariance.
I mean, maybe this is for you easy to see, but for us it was quite tough to get it. But so I mean, the way we got it in the end, the proof is not so long, but for me it's quite unintuitive. Like it really uses this complex structure. But maybe that would be interesting to discuss. Yes. So once you have the harmonicity of the two-point function, you can use the Cauchy-Schwarz inequality and reflection positivity to get also harmonicity of the higher point correlation functions. And from there, it's relatively straightforward to get to the GFF convergence. Thank you very much.